everyone. My name is Tyler McCormick, and today I'll be presenting a container-based GNU Radio development workflow. So, quick little summary about me. So, I am a signal processing engineer at Oak Ridge National Lab, and I've been there for about 2 years now. And a few of my research areas include signal processing and software-defined radio. So, a little bit over the motivation. So, over the last few years, uh, many of our GNU Radio-based projects we've shifted development to use containers, and probably an obvious question might be why. Why would you ruin a perfectly perfectly good development workflow by adding something complex like containers? So, a couple main reasons why: reproducibility, consistency, easier deployment, and simplified development. And the purpose of this presentation is to kind of expound upon those and to kind of basically just show our workflow and why you might benefit from potentially adopting some parts of it for yourself. So before I dive into more of the actual workflow, I'd like to uh, first clear up a few potential any misconceptions um, if you were to compare containers to virtual machines. So on the left-hand side is a very simplified view of how a container, where it sits and how it might interact with the host that it's running on. And on the right-hand side, I have a very simplified diagram of how a virtual machine might sit and how it interacts with the host it's running on. So overall, containers offer only process and resource isolation, otherwise known as OS virtualization. And because of this, uh, when you're running a container, that container has very easy, simple access to a lot of the host hardware. Typically, containers will run a single process, um, and these single processes that containers usually run are also their host processes because the containers are running on the host. And because of this, these processes, there's very minimal overhead for most of these operations. So when you compare a container-based system to a virtual machine, so virtual machines have full hardware virtualization. This means that you're going to need to run a complete operating system with its own kernel inside the virtual machine. This provides very strict, very strong isolation when you compare to the kind of isolation that containers will use. And because of this, there can potentially be significant overhead for guest processes and applications. So, quick summary: containers are not virtual machines, and containers therefore have very minimal overhead, which means you have near bare metal speeds for applications you might be running. You also have very clean access to the host's hardware within the container, and this container also is not required to use all of the kernel namespaces that the virtual machine might need. Um, so virtual machines may provide a greater isolation, but this comes at the cost of increased overhead and limited hardware access. And so overall, you might say that containers provide better flexibility and easier deployment, along with better development and lower overhead. So, quick little overview into a very popular container runtime, Docker. So, what is Docker? So, Docker consists of the daemon itself, and this daemon controls containers. It also consists of the idea of a definition file for building images. Um, it also, lastly, consists of Docker Compose, which can be used for creating and managing services based on images that you have built. So Docker typically runs a single process inside of a container. It's important to note that images must have all the runtime dependencies and libraries necessary to run that process within the container itself, and that all of these runtime dependencies and libraries that you need to run that process are also independent from any of the runtime dependencies and libraries that you have installed on the host. And lastly, Docker tries to isolate the container from the host system as much as possible. Obviously, not as much isolation as a VM might use, but much more isolation than other container runtimes that exist. So a quick little overview into how a container is built. So as I mentioned earlier, containers or Docker, it relies on, is kind of a recipe-based um, build system. And that recipe for Docker is called a Docker file. And a Docker file it might have environment variables that you can define. It may have instructions to copy files or entire directories from the host machine to the container that you are building. It will also have to have commands that will be executed during the build process of that container, and it will also include a command to execute when that container starts if the user does not specify one when they run that container. So as a quick example, in red on the right-hand side, I have shown a very simple Docker file, and this Docker file basically, first off, that from command, it inherits the Ubuntu 2204 base image, and then after that, we run a simple apt update, and then after that, we install the fftw3 library, and then that command that I mentioned that will execute when starting, that we are simply going to execute the bash shell when we start this Docker container. And so actually building the container, so that was the Docker file, and then so you then take your Docker file and you build a container. You start with the base image, and like I mentioned previously, the base image that we're using for this example container is Ubuntu 2204. And in your Docker file, you may want to copy files or projects into your Docker file. Here, I didn't do that, but it, of course, is an option. So something important that will come up again and again when you're working with Docker is that every single Docker file command will result in a brand new immutable layer that will be combined in your final image. And these immutable layers are basically just stacked one after another as the Docker build system just goes line by line through all the Docker file commands. And so, for example, in that previous example that I showed, so that base image that we inherited, that Ubuntu 2204 base image, that becomes a layer. After that, the apt update command also becomes a layer. Then the installing the fftw3 library also becomes a layer. And then that command that will run when the container starts also becomes the final layer to that container. So I don't know how easy it is to see that screenshot. So now that you've built your image, you can turn it into a container, and a container is nothing more than a running image. So like I mentioned, the image is immutable and cannot be changed. And so when you run your image, it becomes a container, and it basically takes that big pile of layers that we showed previously, and it adds one more writable overlay layer so you can interact with your running container. And so once you are running your container, you can interact with it, you can spin up processes or look around. So this little screenshot I've showed, so basically this is the client machine that's running that example Docker image that I showed previously. So the first thing I run is I check and see if the FFTW library is installed, and I have not installed it, and so when I grep for that library, nothing shows up. And so in that next command, I run the container that I just built previously, and then now that I'm inside the container, I then run that exact same command to check and see if the FFTW3 library is installed, and there it is, the output, so it is installed. And the purpose of this is to demonstrate specifically that like I mentioned previously, the libraries and dependencies of your container are always separate from the libraries and dependencies that are running on your host. So now to finally get into the GNU Radio use case. So when you compile GNU Radio from source, it's going to take up a few gigabytes of space. And it's going to take maybe 20 minutes to compile all the dependencies and all the GNU Radio itself, as well as any other libraries such as UHD or anything else. And this takes a while to compile and install. And so what if we could compile everything from source, and but only do that once, and we could basically take that and put that into a base image, and then we could then take that base image, which is all made up of those immutable layers that I mentioned earlier, and then we could If we wanted to add an out-of-tree module that we were developing, for example, we could just add that on top of the base image. Well, the resulting image would be, it'd be very quick. It'd be very quick to install this out-of-tree module we're developing, and it would be much better than having to uh, download, install, and compile GNU Radio from source on every single development machine. And so, um, the reason why this would be really advantageous is that any image that you make can be associated with a tag. And so when you're rebuilding or when you're building a new image that depends on that on the previous image. So for example, if you're building a new out-of-tree module that depends on that base image that we showed earlier, the that base image that we showed earlier, that's not going to change, and so we don't have to compile it again. We can just pull it straight from the registry, and, and so the only thing we have to compile is the out-of-tree module. And so this means that any layers that don't change, those are cached on the build process. And so when we build a new image, those are all cached, and it saves a lot of time. And this caching also exists on the client side. So when you pull an image, layers that have not changed since the last time you pulled, say, the previous version of that image, those remain on your computer, and you only pull updated images. This means that as long as your new layers that you build are not that large, then it is very quick to redeploy your images, so long as the base image doesn't change. And kind of the overall idea of this is that you can basically, compile once and then very quickly and easily deploy and run on multiple clients or endpoints. So, quick little overview of the pros and cons of Docker. So, once you've built your image, to run it on another machine, all you have to have is Docker installed. You can install Docker, and that's a very quick, maybe 2 to 5 minute install depending on your machine speed. And then once you have that, then you just run a command, and you can pull down your image. Like I said, it's easy to deploy. I also mentioned the caching earlier. So, so long as you don't change the base image, it will be cached. And as I mentioned earlier as well, Docker also has the direct access to host hardware, which is great for USB or PCIe SDRs. And because of the recipe-based build system, it's very reproducible. The cons are that everything is isolated by default. And because of this isolation, it means that if you want to access, host folders or host files on the host system inside the container, you'll have to do volume mapping, which, while not too hard, can become tricky at times. And because of this isolation as well, it means that GUI software can be very tricky because of how the X11 server system works in Linux. And also, another unfortunate con is that images are somewhat difficult to move around if you're not utilizing a registry. And because every single immutable layer that we build up is a separate entity. It means that the images can be larger than you might be anticipating, just depending on what you know is inside of each layer. And also, if you're not careful, because the image is immutable, if you make some changes on a running container and then exit that container, all your changes will be lost. So that's something to keep in mind. So in the next slide, I'll do a quick video demo of utilizing basically taking a base image, and then that contains GNU Radio, UHD, as well as all the development and runtime dependencies. Basically, we'll take this base image, and we will add the GR ADSB out-of-tree module to it. We'll push and run this new image on a client machine, and then we'll make a very small change in the GR ADSB code on the development machine. We'll rebuild this image, and we'll push it, and then on the client machine, we'll run it. And this will demonstrate the caching and all the other benefits that I mentioned earlier. Play this. All right. So here we are on the left side. I have my development machine. On the right side, I have my client machine. On the development machine right now, I am going to build a new Docker image that is, and so this Docker image, like I mentioned, is going to inherit the GNU Radio base image, and it will copy into that base image the GRADSB module. It will compile it. And once it compiles, we'll have our new image. And that will not take very long at all. All right, now it's built. And so now, like I mentioned earlier, images are difficult to move around if you don't have a registry, and so we're going to push this image to the registry. And the registry is simply a server somewhere out there that its whole job is to simply just index and collect Docker images that you've made. And so now I'm pushing that image. As you can see, the vast majority of those layers already exist. And those layers that already exist, those are the GNU Radio base image layers that I made the GNU Radio base image from. And so look, it's pushed. So now on the client machine, now we're going to, so that is the command we're going to run the, this is just running the base image. There it is. And then I'm going to just check the about, and this is GNU Radio 310 and maybe 12, I can't remember. So now we're going to close it, and then we're going to go up and we're going to change. Instead of running the base image, we're going to run that container that I just built on the left side development machine. And because that base image is cached, instead of having to pull down the base image again, which is fairly large, we're only going to pull down the deltas. As you can see, the vast majority of those layers are already cached, and there it is. There's our new base image. Not our new base image, but here's our new image that inherits the base image, and there's our GRADSB module. There's the decoder, and that's great. So now we're going to close that, and then on the development machine, we're going to make a very small change to the GRADSB source code, and by change, we're simply going to just make an additional import just to demonstrate how quick the rebuild process is. So here's the dmod, and all I'm going to do is just import time for some reason. And so now that we've made that change, so the Docker build system realizes, it knows that that file was changed, and so when I run this, when I build this version 0.2 of this image, it knows that the only thing that was changed were those files, and so the only thing that's going to rebuild or recompile is the part where we compile the GRADSB module, and there it is, it's built. So now we're going to push that 0.2 version to the registry, and then once it's pushed on the client machine, we'll pull it down, and like I said before, because all that base image as well as all the original layers are cached, the only layers that are going to pull down are is that single layer that we rebuilt. There it is, it's pushed. And now on the client, we're going to instead of running 0.1, we're going to run that 0.2 image we just built. Here we go, and almost all those layers already exist. And there we go. This is that 0.2. This is our exact new version. And then we're just going to close it, and yep, that's it. So now to quickly look into another alternative container framework known as Aptainer. So Aptainer was originally developed as a high-performance computing environment tool. It basically, because of this, the purpose of Aptainer is for enhancing application portability rather than specific, process and file system isolation. And so this means that Aptainer has much less restricted access to the host system that's running on. And some additional features that Docker does not have is that instead of a big stack or collection of immutable layers, images are finalized into a single file that exists on your host's file system. Additionally, images can be encrypted, and this is really neat because Docker, you cannot encrypt your images unless you were to export them to a tar file and then maybe encrypt that later. But to run that image, you'd have to, decrypt that, untar, and then re-import it. Whereas with Aptainer, it has built-in encryption, so you can have an image that is encrypted. You can run it without having to do all those steps that I mentioned. Lastly, there's also very significant additional compression for images that Docker does not utilize. So for deployment with Aptainer, we found that deployment is much easier with Aptainer. So basically, once you've done all your development, all your pushes and pulls, your very quick turnaround cycles with Docker, deployment with Aptainer is where it really shines. So what's great about Aptainer is that you can, instead of having to reinvent the wheel. You can basically build an Aptainer image from an existing Docker image, which means that you can utilize Docker for your development. And like I said, once you have your Docker image, once you're happy with it, once you get to a stable version, then you can combine that into a working or a final stable Aptainer image. And so what's really neat is that the final Aptainer image is very small. So for the GNU Radio base image, and that includes GNU Radio built from source, all the runtime and development dependencies, as well as UHD, that is 617 megabytes, and that's it. And that is like basically live compression. You don't have to unzip anything to run this image. All you have to have is Aptainer installed on your host machine. And so, like I mentioned previously, some of the because Aptainer has less strict isolation, it's much easier to run things and access hardware and access host folders and files inside the container. You basically don't need volume mounts anymore. It just kind of has direct access to everything. And the idea is you basically can just push this image file to your host and just run it. So few of the Aptainer pros and cons. That single file that I mentioned, it's an actual real file that lives on your hard drive versus Docker, which is this kind of esoteric collection of immutable layers. It has very minimal isolation, which means that running GUI apps is much easier than running, because with Docker, that means you have to map over all the X11 stuff, and because Aptainer has much more direct access to the file system, you don't have to do that. And all those, Aptainer essentially has all the benefits of Docker, including better compression, encryption. One big downside of Aptainer is that it does not utilize a cache build system like Docker does, which is why we found that it's much better to do your rapid development with Docker, and then once you've gotten to a stable version, and then you basically deploy with Aptainer, because if you had to rebuild your Aptainer image every time you made a simple change, you'd be there all day basically. So now doing a very simple Aptainer demo, I'm basically going to take the GNU Radio base image that I showed earlier, and we're just going to launch it and show how much easier it is to launch it compared to Docker. So here's the client machine, and so first I'm going to do an ls-lh to show, and maybe hard to see, but I promise it is only 617 megabytes. And so now, instead of that long, gross Docker command with all those volume mounts, it is simply Aptainer exec, the name of the file, and then the command you want to run. So here I'm running GNU Radio Companion, and so there it is. And like I said, this whole image is GNU Radio Companion, all the development dependencies, UHD, in 617 megabytes. And as long as you have Aptainer installed, you can run this. So, and here's a little more in-depth comparison. That's what I mentioned. There's that really long, gross Docker command. And the reason why it's so long and gross is that, like I mentioned, Docker has really strict resource and file system isolation from the host. And so anything you want to access, such as X authority files or other X11 required files, you have to specifically map over. Whereas with Aptainer, that is not the case. It already has access to that stuff. And so you can simply just run the container, and you don't have to worry about getting your X11 volume mappings just right. So in conclusion, synchronizing GNU Radio development environments across lots of different machines, especially if they're running different operating systems or different versions of Linux, can be very tedious and is often non-trivial. And Docker can help with this by decreasing development time and simplifying distribution both during and after development. And then once you've done all your development, Aptainer further simplifies this process by applying that additional compression and decreasing image size and improving your host device access, so being able to access USB and PCIe devices much more easily than you can with Docker. Thank you, and if there are any questions, I'll take them.